Neural networks simplified covering RNNs, GRU, LSTM and bi-LSTM. So what are neural networks? So the neural networks are computational models inspired by the structure and function of human brain. They consist of interconnected neurons that process and transmit information hierarchically. And these networks can be trained to perform a wide range of tasks such as image recognition, speech recognition, and natural language processing. Imagine a network of interconnected friends, each with their own sets of skills and knowledge. So when a new task or problem is presented, the network processes the information through a series of steps, much like how your friends would collaborate with you to solve the problem. So here the input is a set of data points such as image, sound clip or a sentence. Then the hidden layers, the data flows through a series of hidden layers where each layer contains a set of interconnected neurons. And these neurons perform computations on the input data, extracting relevant features and patterns at each state. The number of hidden layers and neurons can be adjusted to suit the task at hand. And then we have activation function. So at each neuron, an activation function is applied to the weighted sum of the inputs. And these functions introduce non-linearity into the network, allowing it to model complex relations between the input and output. And finally, we have output. So the final output is a prediction or decision based on that information produced or processed through the network. So in summary, neural networks are like a group of interconnected friends, each with their own set of skills working together to solve problems and make decisions. And these networks can be trained to perform a wide range of tasks by adjusting the weights and biases of connections between neurons. So today we'll discuss some popular networks including LSTM, that is a long short-term memory, bi-LSTM, then recurrent neural networks, gated recurrent unit. So let's get started. First is your long short-term memory. Imagine you are trying to learn a new language. So as you progress through lessons, you learn new vocabulary and grammar rules. You see this knowledge to translate sentences and understand their meaning. Your brain stores this information over time and you recall it when needed. In the same way, LSTM neural networks are designed to process and remember information from a sequence of data such as time series, text, or speech. They are particularly useful for tasks that involve understanding the relationships between elements in a sequence, like predicting the next word in a sentence or identifying patterns in a time series. To understand how LSTM works, let us consider an example with a simple sentence. I love to play guitar. So here the input is a sequence of words which is fed to the LSTM, one word at a time. Then comes the memory cells. LSTM layer has a memory cell that remembers the most important information from previous word in the sequence. It keeps track of the relationship between words and learns when to forget or update this information as new words are encountered. Then it has gates. This LSTM uses gates to control the flow of information into and out of memory cell. There are three gates: input gate, output gate, and forget gate. Now what is input gate? So this gate decides which new information to let in and update the memory cell based on current word. Then comes the forget gate. This gate decides what information from memory cells should be discarded or forgotten. Then output gate. This gate decides what information from memory cells should be output as the current word representation. And then we have an output. So the LSTM layer outputs the final representation of current word, which is then passed on to next layer of neural network for further processing. So in summary, LSTM is a type of neural network designed to process sequence of data by remembering important information and selectively updating its memory as new data comes in. It's like a language learner who keeps track of the relations between the words and uses this knowledge to make prediction about the next word in a sentence. Then comes the bi-LSTM or bidirectional long short term memory. So this bidirectional long short term memory, it's a variation of this LSTM, which is a type of neural network that processes sequential data. Now, bi-LSTM is useful for tasks that require understanding the context of word in a sentence, such as sentiment analysis or language translation. To understand bi-LSTM, let's continue with the example of simple sentence, I love to play guitar. So if we talk about unidirectional LSTM, so the unidirectional LSTM will process the sentence in a single direction, either left to right or right to left. So in the left to right direction, this LSTM process each word and update its internal memory cells based on the previous cell. For example, we are talking about I love to play guitar. So when processing this sentence, the word guitar, LSTM takes into account the context of previous words, that is I love to play, to better understand the sentiments expressed in the sentence. While when we talk about bidirectional LSTM, now this bidirectional LSTM, it will process the same sentence but in both directions, left to right and right to left simultaneously, which allows the LSTM to capture information about context of words from both directions. Now when we talk about left to right direction, so here the LSTM will process the sentence in the same way as the unidirectional LSTM, which is updating its internal memory based on the previous words to understand the sentiments expressed in sentence. But when we talk about right to left direction, so here the LSTM will process the sentence in reverse order from right to left. This allows it to capture information about the context of words from the future, providing a more complete understanding of the sentence. And when we combine both these representations, so the final representation of each word in the sentence is obtained by concatenating or combining the left to right and right to left representation, which creates a more robust understanding of each word's context, as it takes into account the information from both the past and the future. So in summary, we can say bi-LSTM, it's a variation of LSTM that processes sequential data in both directions, left to right and right to left, to capture the complete understanding of the context of each word. And this can be useful for tasks like sentiment analysis, where understanding the context of word is crucial for accurate prediction. Next comes the recurrent neural network. Now this recurrent neural networks are a type of neural network which is designed to process sequential data such as time series, speech or text. Why they are called recurrent? Because they have feedback connections which allow the information from previous time steps to influence the current computations. Imagine a simple card game. Okay, so where in each round you are dealt a card and based on your card you have to make a decision. So RNN works similarly. It processes input in a sequence and make decision based on the current input while also considering information from previous steps. It has an input which is a sequence of data points such as time series of stock prices or sentence. Then it has recurrent layers. Now this recurrent layers is the one where previous steps is fed back into the current step, and this feedback loop allows RNN to maintain a memory of sequence and make decision based on the entire content. and then it has activation function. So at each step an activation function is applied to the weighted sum of inputs and the previous memory. Now these functions introduce non-linearity into the network, allowing it to model complex relations between inputs and outputs. And then we have output. So the final output is a prediction or decision based on the information processed through the network, taking into account the entire sequence. So in summary, we can say RNNs are like a player in a card game, where each round they receive new information, making a decision and remember the previous decisions to inform future actions. So this memory of past information allow RNNs to effectively process sequential data and make accurate predictions. Now next comes, how can you calculate this RNN by hand? So even though RNNs were not originally invented for computer vision tasks, I believe it is important to practice calculating an RNN by hand to gain a good intuition about how an RNN processes a sequence. So let's get started. First we'll have a walkthrough. So here we have given the hidden states which are initialized to 0, 0. We have the first input x1 and the hidden state 0, 0. These are linearly combined using weights A and B, followed by a non-linear activation function ReLU to calculate the new hidden states. Now this hidden states 3 and 6, these are linearly combined using the weight C to obtain the first output, and we'll repeat the steps 1, 2, 3. So its properties are like this parameters. So the same set of parameter metrics A, B, C are reused to process each input token. This is the main reason why we use the word recurrent, and then sequential. So an RNN sequentially process each input token and produce each output token in return. An RNN cannot process all tokens in parallel. In contrast, the transformers can process all tokens in parallel. So let's start understanding it using this diagram. So here we are given this input 3, 4, 5, 6. So just write here 3, here written 4, here written 5, here written 6, right? Just take this matrix, this both parameters A and B, right? Here written 1 by 2, here taken this matrix, here taken C. So this is your B, this is your A, and this is your C, right? So first of all, we'll have multiply the 0, 0, right? So nothing will come, right? Next, just multiply this like this, 3, and then comes your 6 here, right? How will this come? So in order to understand this, like first we have given like this key, here it is 3 here, right? 3 into 1. So 3 into 1, that is 3. Then 3 into 2, right? 1 or 2, like this. Okay. So it is given 3 by 6 here. Now we have here given the next output. So we have just written the 3 by 6 here. Now check this one, 3 and this much. So it shall be minus 3. Now we will take this one, minus 1, 1, and we'll take this 3 and 6 here. So it should be minus 3 plus 6. It shall come out as the 3 here, right? Now next, in the next stage, we have 4 here. Now this 4 will be added to this 1. 4, right? You have taken just remember 4. Then we will add the next thing. So in this stage, now 3 minus 6, right? So here we have taken 3 minus 6. So it should be minus 3 here. So 4 minus 3 should be 1 here. So it shall be 1 here. Now take next stage, 4 into 2. It should be 8 here. Now we will multiply it with the lower things like 3 plus 6. That should be 9 here. So 8 and 9, it should be 17 here. So next comes a 1 by 17. these all are positive here, so we'll return 1 by 17. Now there is, take this 1 by 17. Now have this multiplication with minus 1 and 1. So minus 1 plus 17, that comes out as a 16 here. So it shall be 16 here, right? Now in the next stage, we'll take this 5 here first. Okay, so 5 into 1, 5. Okay, then we'll do the things with this 1 and 17. So 1 minus 17, right? Minus 16. 5 minus 16, that is minus 11 here. Now in the next stage, 5 into 2, that is 10. Remember the 10. Then 10 and then 1 and plus 17, that is 18. 10 plus 18 is 28 here. Now it is minus 11. So it should come out as a 0 and 28. Now we have 0 and 28. Now multiply this with minus 1 and 1. So 0 into minus 1, 0 plus 1 into 28, it's 28 here. Now next comes a 6 here. So we will consider the 6 into 1. So 6. Now remember this, we will multiply with 1 minus 1. So 6 plus 0, right? So in the next we will get it as the next stage, right? So here we'll get it as a minus 22 and the 40 here. Then we will take this 40, we'll multiply this with this one, and then we will get the final outputs like this. So to summarize this, how we do, first take multiply this with this one, like here we have taken 3 and then taken this, we multiplied both these things, rows and columns, right? 3 plus like this, so we have taken it like this, right? And then we multiplied this with this one. Okay. Then comes your gated recurrent unit. Now this gated recurrent unit is a type of recurrent neural network that is similar to LSTM but simple in structure. It was introduced to address the vanishing gradient problem, which can occur in traditional RNNs, making it difficult to train for tasks with long sequences. And this GRU is designed to effectively process sequential data by selectively updating its internal memory cells. Imagine you are learning a new skill, such as playing a musical instrument. So as you progress, you learn new skills and refine your skills based on your past experience. So here also, this gated recurrent unit works similarly, but instead of learning musical techniques, it learns patterns in sequential data. So it has input, which is a sequence of data such as time series or sentence, which is fed into this gated recurrent unit layer, one element at a time. Then it has update gates. So the GRU has an update gate that decides how much of the current input should be incorporated into the memory cell and how much of the previous memory cell value should be retained. So this update acts like a refresher that selectively updates the memory cell. Then we have reset gate. Now this reset gate determines how much of the previous memory cell value should be forgotten and replaced with the new information. So this reset gate acts like a reset button which helps the network focus on the most important information. Then we have memory cell. So the memory cell is the brain of gated recurrent unit, storing important information about the sequence. And then we have output. So the final output is the representation of current element in the sequence, which is a combination of updated memory cell and the information from the update gate. So in summary, gated recurrent unit is a type of recurrent neural network that uses gates to selectively update its internal memory cell. It simplifies the structure of LSTM by combining the input and forget gates into a single update gate and removing the output gate. This makes this gated recurrent unit computationally efficient and effective at processing sequential data. Thank you.